Okay, so hi guys, how are you guys doing today? Good, perfect. All right, so did you guys all watch my several lecture videos on YouTube YouTube channel? You guys are good? Okay. So we're gonna follow up to the one we left last Friday. So it was we was working on. Oh, by the way, I'm still working on the syllabus because I got the Cengage course onto my account. I'm still navigating it. So once I find them, I'll post the syllabus. So I think it'll be posted by tomorrow. Okay, so you can see that at least first year of the syllabus by tomorrow. Okay, but I all said the exam policy and everything in previous lecture video on YouTube channel. But you can also watch it. But it'll be up by tomorrow anyway. Okay. All right. So I just want to review just a little bit more from the last previous lecture. Was about this one. So whenever you have some like a hydrocarbons, so you can count the numbers in carbons over here. Okay. So maybe you have 5 of them, and then I try to do this. Okay. But as you know, you can always draw like this skeletal structure like this. It will be the same thing. You guys know this, right? Okay, perfect. Just let me know if you have any questions. Okay, so all you need to do is just try to the carbons in the longest possible chain, which is 5. So I'm just gonna put the base name over here, which was 10. And obviously this is arcane, right? This is arcane. So we're gonna put the A and E at the end to make it pentane. That's what it's the name for. Okay. So this is the base. This is your suffix. Okay. This is where you can put the prefix whenever you have some substituting groups. So for example, I can put 1CH3. Okay. So if you look at this one over here, this is just 1 carbon. So this is just the same as methane, right? Just 1 carbon A&E. But this is a substituting group, so we're gonna put this as our alkyl group. Okay. So what you can do for this one, you have a substituting group, only has 1 carbon in it, and this is methane kind of group there. And what we're gonna do is we're gonna put YL. So it makes one of the substituent alkyl groups. So we call this methyl group over here. Okay, makes sense, right? So far, we good? Okay. So I'm gonna put not methane but methyl. So it's as a one substituent alkyl group here. And now, only thing you have to do is locants. So now you want to point out where that is, right? So to do that, you need to number the carbon. So you need to number the carbon from here: 1, 2, 3, 4, 5. Or you can do the other way: 1, 2, 3, 4, 5. Okay. So if that happens, either way is fine, but always choose the lowest possible number. In both cases, for this one, it's just 3. So you can put 3 methyl pentane. Okay. Sounds good, right? Okay. So that was what we did the last lecture. Okay. So you can also check it again, the last Friday lecture on the YouTube channel. But this is what we left before. It makes sense, right? Okay. All right, so like I mentioned before in the Friday lecture, we're gonna do one more bit tricky one, and we'll move on. Okay, so it's not that tricky. If you can just, okay, 1, 2, 3, 4, 5, 6, 7. Okay, so I just counted them. There are 10 carbons in this structure here. So that will be D, right? And we're gonna put A and E too. So be decaying. here. And what you can do is you can try to put 2 methyl group instead of 1, maybe at this time. So still, this is our longest carbon chain. So this still can, okay. And then we can try to number them. So here's a carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. Okay. Right. So in this case, what we're gonna do, we have a 2 methyl group instead of 1. So we can do, we still gonna do methyl groups, but we have 2 and 3. So we're gonna put 2 numbers, not 1. So it will be 2, comma, and 3. And please make sure you do dimethyl, because you have 2 methyl groups on this carbon chain. So what you can do is you can put a locum for number these 2 numbers, and you can put the methyl group, but make sure you put the di. That means there are 2. So it will be 2, 3 dimethyl decene. Makes sense, right? Okay. So now what I mean by a bit tricky part is you may have nice, just linear, good substitution group, but sometimes you can have something like this. Okay, something like this. Okay, so what happens to this substitution group is this is also kind of branched out. Okay, so it's kind of hard to name right now. So what we can do is this one. You can consider this one as kind of one independent compound, or you can say just some alkene groups there. So I'm gonna ignore this one for now. Okay, I'm gonna ignore this one for now. But let's say we have just this one. Okay, just this one. Okay, just for now. So still, we're gonna do the same thing. What you need to do is you need to find the longest carbon chain over here. So the longest carbon chain is what? 3. Either here or here is still 3. Okay, makes sense, right? So if there's a 3, there will be prop. Okay, right? And this will be still alkanes of propane. But we have a 1, 2. Doesn't matter which way you can count the carbon from, left or right. Still 1, 2, 3, 1, 2, 3. And it's almost same as you have a methyl group at 2, right? So this is in carbon 2, carbon 1, carbon 2, carbon 3, right? Okay. So this is the 2. This methyl group in carbon 2. So we 2 methyl propane, right? So far so good. Okay. So then we put this as a whole group, and we're gonna now consider this one as a alkyl group. So what I'm gonna do is I'm gonna change this one to Y. Okay. Okay. So this is so now you can change this whole thing on where? Where? It's carbon 6. Okay? Right? So what you need to do additionally is what? 6. And then we're going to copy 2 methyl propyl and what? Okay? That kind of makes sense. We good, right? Okay, good. So as you know, this is kind of a official way, formal way to name this alkane. So you can do this way. Okay, now we got how we do this one. and make sure this group also count as a whole as a group. You still count them as the M, alphabetical order for your substituting group. So this comes first and later, this is the M here. Okay? And make sure, do you guys remember this? Do you guys watch the Friday lecture? This one doesn't count for alphabetical order. You didn't. Di, tri, tetra doesn't count for alphabetical order. Okay, so just make sure you guys do this one here. And here's a question. Is there any better way to put this in a common name? Yes, we do. So if you look at this one over here, I just did this one, that's fine. But this is maybe too long, too complicated. So maybe you can think about some common name for this one. And if you look at this one here, there will be in total, how many carbons there? 4, right? Perfect, 4. So technically this is a butane in a whole, but it's not a linear. Okay? So there's a 1 carbon sticking out among the 4. There's 3 are in a line. So 1, except 1 carbon, they're in a line, right? In a carbon chain. So in this case, we're gonna call this isobutane, but we're gonna change this one again, alkyl group. So you can actually put this as 6 isobutyl. That's much easier, right? It's just because when you count the total carbons in this substituting group is 4, but it's not linear. It can be just butyl, but isobutyl because there's 1 carbon sticking out from the longest chain. So we call this iso. Okay? It's just we named it that way. Okay? So in this case, this isobutyl here group, and here's the thing. This is quite important here. Okay? This is quite important. And it's isobutyl here. In this case, you count this I in your alphabetical order. You count it as I, not B, I. Okay? So in this case, you're actually going to put in different order. So it's not just this. You're going to put this group later than this one. Because I comes first in alphabetical order than M. Okay? Still, D doesn't count. You remember that, right? So in this case, it will be 6 isobutyl, 2, 3 dimethyl decane. Is it too much? No, we good? Oh, perfect. Oh, you guys are great. That's awesome. So this is you can always do this way. You can look at this one here. So now this is we just talked about the isobutyl here. You can do this one, okay? Okay, this one. So now you have now you have still. Could you count the numbers of carbon here? How many? It will be 1, 2, 3, and 4, right? Perfect. In this case, what you can do is, if you look at this carbon over here, okay, this carbon in this alkyl group, it has a bonding to this carbon and this carbon here. Okay, so this is a secondary carbon on this alkyl group here. So in this case, it's not isobutyl now, but this will be secondary butyl. So we're gonna call this sec-butyl, or you can also put this as butyl. Either way is fine. So one more problem you can get, like this type of part of chapter 3, is how about this one? Still, there are 4 carbons in total, but this carbon is bound to the other 3 carbons in this alkyl group here, and that is tertiary top butyl, or you can say T butyl. That's the only difference. So when you look at this one independently and see how many carbons are covalently bound to that carbon that link to your main base, and then you can do the second and third based on degree of the carbon. It says, yeah. Does it make sense? Okay. So, here's one more thing I want to mention here. Whenever you have secondary sec or tertiary tert or T butyl, in this case, we write those in italicized. So it's not just like this, like this. Okay. I'm not great. I'm sorry. This is I can do. Can you see that? It's like a lean. It's like italicized. Okay. So this is why except the iso right here, this S and T does not count as alphabetical order. Just B is the alphabetical order for this one. But iso, we do count I as alphabetical order. So this is very important. I think this is something you need to remember, because it's just the way we name the alkane. Okay. So I think this should be good enough. I think, because we're gonna have enough time later about even other type of compounds later. But for alkane wise, this should be all you need to know. That's it in chapter 3. This should be just fine. Okay. So I think that's pretty much. Do you have any questions? We good? All right. So let's move on. Okay, so before we move on to next part, I want to just give you one brief information about isomers. Okay, you'll see this is isomer. You can say isomerism, but it will just get isomers. Okay, do you guys know what the isomers are? What is isomerism is? You guys have done this before in previous courses, right? JK 1 and 2, you guys remember? Okay. So isomers is normally we meant by all the compounds that has same chemical formula. Same chemical formula. So if that is butane, right? There will be C4H10. Do you guys remember this, right? CnH2n plus 2. You guys remember this? Okay. So this is how we can, But even though we all have the C4H10, it's not all same. So let me show you. So whenever you do this, it can be mainly categorized in two parts, mainly. So the first one is, we have two names for this one actually. The first one is constitutional isomer. Constitutional isomers. Or you can call this structural isomers. So here's the thing. Whenever you think about structural isomers or constitutional isomers, that means they're different in structure. So here's the thing. Whenever you have two compounds with the same chemical formula, but they're structurally different. So if the way we can define this isomers in certain compounds is you need to number carbons, into numbered carbons. And between each carbons, what kind of bond is made in these two carbons will determine it is constitutional isomers or Stereoisomers. Stereoisomers. Okay. Here's the thing. I can show you. So if you have a butane like this, as I mentioned before, you can number the carbon 1, 2, 3, and 4. Okay? So I just number the carbon here. And as you can see, there's a single bond between 1 and 2, single bond between 2 and 3, and single bond and 3 and 4. Right? Good? Okay? How about this one? Okay? So if you do it in this way, you have a single bond between 1 and 2, but in carbon 2, how many single bonds are there? 3. Right? So in constitutional or structural isomers, the bondings between carbons, 2 carbons, this is different. So whenever you number the carbons in the compound or alkane and count the numbers of the bonding, what type of bonding there are between each 2 different carbons, and if they're different, we can call them our constitutional or structural isomers to each other. It makes sense? We good? Okay. So that means for stereoisomers, they also share the same bonding as well too. So not even just the chemical formula, but also bondings between atomic composition, like even carbon, hydrogen, any atoms in the molecule, the bondings between those, each atoms, number the atoms, either carbon, hydrogen, or anything, are still the same, but still different. Here's are 2 different scenarios here. So this is something we're gonna do in the later chapter, so I'm gonna only tell you briefly. Okay, this is optical isomers. Optical isomers. You call this sometimes enantiomer, but anyway. And then this is just simply a mirror image of something. So if you have some center here, you just draw the mirror image on this one. Okay. So that is possible, even though when you have a mirror image, but still not the same thing. But obviously they share the same bonding between A and B and D and F and C. This whatever those the groups are around the central carbon. And then if they have 4 different groups bonded to the central carbon, whenever you have a mirror image, there are going to be still different compounds, even though it's just a mirror image of it. And we call them optical isomers. We'll get this to, I think, chapter 5, but anyway. And the other one is, don't want me the double bond. So we call this geometrical isomers. So whenever you have a double bond, here's the thing. First thing I emphasized in chapter 3 when we talked about alkane is their freedom of rotation of single bond, right? They can always so if this was a single bond, you can just rotate, right? So they can make it this one, no problem. They can just rotate the single bond, but they cannot rotate the double bonds. So that means if there is a position set by each side of the double bonds like this, they just stand still that way. They cannot rotate like this. There has to be either this or this and set still, because the double bond can rotate it. Okay, so this is why we have a trans and cis or D and E, those type of the geometrical isomers. This is also we'll do later in the chapter, but most of the time in chapter 3 it deals with the these isomers for physical property. So I'm just giving you a bit of a heads up for the coming chapters in this semester. Okay, so but I at least want you to know this one in your mind. Like we have a certain isomers group can be grouped like this, and we're actually going to talk about this one today in chapter 3. But later we'll do more in later chapters. Okay. All right. So does it make sense? We good? Okay. Just let me know. Okay, so why does the structural constitutional isomer so important here? Because sometimes it actually governs some physical property of the alkane. So one of the good example you can see in your PPT slide is pentane. So as I mentioned earlier, there can be a lot of structurally different constitutional isomer or structural isomers. So the easiest one would be obviously just the linear one. I mean, it's not linear, but you know, the chain in a chain. Or you can do something like this, okay? And you can do something like this one as well too, okay? Something like this. Okay? So here's the thing. The first one I want you to remember for kind of boiling point wise is whenever you have a longer and heavier hydrocarbon alkane, they will show you the higher boiling points. It's just simply because of this one. So whenever you have bigger, like a heavier, just molecular weight wise, it's heavier, right? Okay, and then they tend to be more stay as a liquid phase because it's heavier. Okay. Let me give you one example. So whenever you have a box filled with metal beads, okay. I don't know how big they are, but they're pretty heavy metal chunks are stored in this container. And if you have, it's kind of dramatic knowledge, I'm sorry, but if you have a box filled with a feather, okay, feather, and I'm more for joy too, sorry. Whenever you have take a blow on the surface, this will float up into the air. This is a lighter. But this one will not, probably maybe one small tiny particle, but most of them will stay in the phase they're already in. So that means it's actually kind of makes sense that it becomes bigger and heavier. We need to have higher energy to get them into the more kinetically high status, which is gas phase. So the high energy I mean by that is heat energy. Right? Heat energy can be transformable into kinetic energy, so they can have a much higher kinetic energy, so they can move much freer and more energetic. So they can be more in the form of gas phase, which they can enjoy a lot of space among them. But for this one, we need to have a more high energy. By mean, we have temperature for this one to be boiled or to be in gas phase. We need to have a much higher heat energy will make you a much higher temperature to make it happen. So if it is bigger and heavier and for your compounds, they tend to have a higher boiling points. Kind of makes sense? Okay? So what about the structure isomer then here, which is this one? Whenever, do you remember intermolecular forces, right? The interaction between molecules. If you have addition like this, you can do this. That means they're increasing surface area, right? So they have a more chance to interact on the whole parts of their compounds. So they ensure makes bit much more stronger interaction among those. But if you have something like this one, there's the compounds can contain only limited parts of their surface. So interaction between those alkane will be weaker than this one, relatively speaking. So if these ones can be holding each other much stronger, same thing happens. We need to have a higher energy to make it more separate them in a bigger space, which means what? They'll be more likely in a gas phase. So those structural isomers can also sometimes give you some change in their physical property when you consider one of them as boiling points. Okay? So if it's more like a longer and more like in a linear shape and as a same chemical formula for your construction isomers, this will tend to have a higher boiling points. This tend to have a lower boiling points. It's just because of the exposure, how much they can involve into those intermolecular interactions. It makes some change in their boiling point measurements. Okay? Make sense? Okay? This is actually slightly, you did it somehow at the later part of thinking too. But we do it more precisely this time for alkane. Okay? We good? Okay. All right then. Okay, so let's do just one practice problem because we want to find out how we can do this. So maybe I should give you one. Okay. Okay, 1, 2. Okay, like here. And then can you guys possibly name? I'll just do this again too. So let me do this one more time. This is a bit different, but we have 1, 2, 3, and 4, and 5, and 6, and 7, and 8 over here. Okay. So we find the longest carbon chain, which contains 8 carbons. So we obtain. So we just did the base and the suffix. Oh, that's pretty good. But we have also some branched. So yeah, go ahead.
Is there any way that you could move your computer down? I can't see the board.
Oh, really? Okay.
Your computer.
Yes, absolutely. Yes.
Thank you.
I'll just do it.
Yes, sir.
Is it better? Okay,
Yes, sir.
perfect. So it should be okay because the camera should be okay. So if this is the some branch substituting like this one, what you can do, okay, what you can do is you can do the same. This is a bit tricky, so I'm just gonna do this for you. Let's try some practice problem maybe on Wednesday. In this case, we're actually gonna do this in they actually link to this carbon. So longest carbon chain from here is actually not the 3 because it starts from the middle, not the end, right? You see it's linked to the central carbon. So longest carbon chain is actually 2, not 3. So it makes 1 methyl ethane. Just this one, okay? I hope that makes sense. Because even though there are 3, but it's linked to central, so from here is some longest is 2. So this is why we put this one in here. So we can put 4, 1 methyl and ethyl. Because now we put this as alkyl group as a substituent group here, ethyl, and we just put octane. Okay. So that's good, right? But also what we can do is you count this whole compounds. There are 3 carbons, so it's technically propane, right? It's propane, but obviously it's not like just the propane group because there's one sticking out from the 2. So this is what once again we do isopropyl. Okay, so this is the same as 4 isopropyl octane. So this is just another example. Actually, I wanted to give you as an example practice problem today, but I think I need to do this because it's now actually in the propyl groups. So yeah. Okay. Oh, just one more thing. This is also important too. So some maybe think that if there's any, so this is carbon here. This is a bond to carbon 2. So sometimes maybe you can do is what? Oh, maybe I can do secondary propyl, right? As propyl, but don't do that. We don't do it for this one. We just do have isopropyl. That's it. We don't do. We only do second, third since we have more than 3. So it'll be 4. Okay? Does it make sense? So we don't have a sec propyl. No, just isopropyl is fine. One sticking off from the longest chain is iso, which is the same as the secondary propyl, but we don't do secondary propyl. We only do isopropyl. Does it make sense? Sometimes it might confuse you. I just told you in butyl that there's 2 degree secondary, 3 tertiary. Well, but this one is secondary now. We just don't do it in chemistry for propyl groups. It's too small to do it. Okay? Okay? Because there's no part and anyway. Oh, I'll just stop. All right. So that's pretty much it today. So thank you guys. I'll promise I'll do a bit more practice on this one, and we'll try to finish up the chapter 3 on Wednesday. Okay? Maybe some later in the Friday. Okay?